Welcome back, physics fans. Here we are on day 8 on graphing, or it's actually grade day 9, I believe. Position time graphs. Now, position time graphs, I get lazy and call them distance time graphs. I get lazy and I call it DT graphs, and then I'll call it velocity time graphs, and then acceleration time graphs. But when I'm talking distance time graphs, I'm actually talking position time graphs. And you can try to correct me every single time. What's the difference between position and distance? Well, distance is how far you have traveled, where position is your location with regard to the origin. Distance is always increasing. If you go to the store that's 2 kilometers away and then come back home, you've traveled 4 kilometers. Distance will never go backwards. But position will go backwards because you're back at home and your position will be 0. Okay? So in position time graphs, if you're sitting still at a certain time, which is constantly moving along, as it's, we're not going to stop time as we watch here. If you're not moving, your position stays the same. Your position stays the same. And if you're moving, then this position is going to go up or down. So if you were moving, we would expect maybe it's going up, and maybe you're going back down. And so as you do it. So let's just take a look at a visual representation here. Here is a little Java app that I use called the Moving Man. Okay, let's try to fit this into the screen that I'm recording. Move it. And there we go. So the Moving Man, I can type in a number here. Maybe he's at 0, the origin. Or he could be at -8 position. He's at the tree. If you want to put him at the house, that would be a position of 8. Okay, and his velocity I could type in and I could hit 0. So I'm going to hit record. Let's see what the graphs look like. So he's going to be positioned at 8 and with no velocity, and it's probably what you probably would expect. His location is not changing. That's his position time graph, and his velocity is just 0. Okay, I can play that back, and we'll stop it at the 2-second mark. I'm going to now change what happens at the 2-second mark. So he stayed without moving for 2 seconds. And now I'm going to put a velocity of -2. So his velocity is going to go -2, and he's going to start moving negative. That means to the left here. And it's a no-brainer. We can understand what's going on. And I'll stop it when he reaches the tree. There's our velocity, our position, and it's moving. And it keeps on going until it reaches the tree, which is at -8. His velocity was -2 all the way along. It didn't change. There was a change here. It just had to connect it straight down. So instantaneous change straight down from 0 to 2, because I just typed it in. And he moved. Okay? So this is a negative slope in math. It's going down and represents the negative velocity. In fact, we could say that this was over up to 10 seconds here, and this was 2. Okay, so let's just screen capture this and do it or I have to go down here to get the time. Now I can draw. This is at 10 seconds, 8 seconds, 6 seconds, 4 seconds, and 2. The run here, right from there, that is 8 seconds. And that's the run. The rise Well, it actually wasn't a rise, it was a lower, but we'll call it the rise still. It went down from positive 8 down to negative 8. So this went down 16. So that is the rise. So if I do rise over run, and that's how we get the slope. We get the rise of negative 16 over the run of 8. Now let's just actually put in the units as well. This is position, which is in meters, and this is in time, which is in seconds. We get a negative 2 meters per second. And hey, that was the velocity. The velocity I typed in is negative 2. So the slope of a position time graph is the velocity. Okay, this is our number 1 rule. We're going to have 4 graphing rules when the 2 chapters are up. Chapter 1 that we're on and chapter 2 that we're going to be doing next chapter. There's going to be 4. Right now we're going to just only have 2 rules today. Maybe not even 2. Maybe we'll just have 1. The slope of a position time graph gives us the velocity. Okay, that's our rule. Let's just verify that by continuing to play here. At this time, I'm going to change the velocity. And let's make the velocity 4, positive 4. So now this red line is going to jump up to right up here and start drawing as a positive 4. And this blue line is going to have a slope of 4. So we're at 8, negative 8, and in 2 seconds, it'll go up 8. Every second, it'll go up 4. So over 1 second, up 4. Over another second, up 4. So we'll anticipate it to go right through that point there, the 0 point there, and then continue on up until it reaches 8 here. So let's just play it here, record it. Whew. So this is a slope of 4. A positive slope of 4. So it goes over 4 seconds. 1, 2, 3, 4 seconds. And it goes up 16. Or over 2 seconds, it goes up 8. So 8 divided by 2, that's a slope of 4. And it is. So the slope of that position time graph, slope of the position time graph is our velocity. And if I gave you the velocity, you could graph this. So this is a two-way representation that we can do it. This is a little bit thinking now. If I showed you just the red line graph, the velocity, and say to start at 8, you'd be able to say, oh, okay, for 2 seconds you didn't move. So I draw the blue line straight across. And then you go for 8 seconds, I was moving at negative 2. So I draw a slope of negative 2 for 8 seconds. So you could draw this total blue line by knowing the red line. But you also have to know where to begin. So I say at 8, then go ahead. And you could go the other direction. If I gave you just the blue line here, the position time graph, and you could measure off of here, you go down across, oh, that's a negative 2, so you draw a negative 2 line. And this is a slope of 4, so you could draw a 4 line. Okay? But if you're looking at just this red line, it's really hard, and if it's just the red line, you could not determine when the person was back home. Here he is back, well, at the origin, 0. And this is at the origin, 0 there. At these 2 points, at a time of 6 and a time of 12, he passes by this point up here, the origin. Let's just replay this. And you'll see this. Okay, I'm going too slow. Let's speed this up. So all of a sudden, he's going to pass the origin right there. Bam! And then he bounces. Bam! He passes the origin at that point. Okay? If you look at the red line here, you can't tell that he's passing the origin here. You can't tell that he's passing the origin here. You'd have to calculate it out. Any questions about this? So let me just capture this and reteach that. From a position time graph, you can get its position. So he was at 8 here, and he was 8 here, which is the house up top, and he was at 8 here. So position time graph, you can get position. You can see that he's changing the origin here, but you can also get its velocity. As we've just figured out that we could calculate this object's slope, and that's a -2 slope, rise over run, and we get its velocity. So not only you can get position from a position time graph, no duh, you can get position from it, but you can also get velocity because of slope. On a velocity time graph, you can tell me its velocity, but you can also find out its change in position. Okay, once more, here we go. This is a velocity of -2. A velocity of -2 times this 4 seconds, no, 8 seconds, sorry, 8 seconds. So you know the velocity of 2 and the time of 8, you can get its displacement. The displacement is velocity times time, which is 2 times 8, which is -16. Actually, it was a -2, right? So you could get its displacement as -16. And we know that because it started off at 8 and went down to -8. So, but if we didn't have this blue chart, if we didn't have that blue chart, we could still look at this red chart and go, I could take the velocity and multiply it by the time, and I can get the displacement. And if those people that are into geometry, you'll see that this area here is just that. That is base times height. And that's going to be the area. And that happens to be the change in position. The change in position. So that is going to be our second rule on graphing. Okay? The area, and now I just use the terms under a velocity time graph, is the change in position. Okay, and that's going to be our number 2 rule. Now, it's really, really, really cool that this rule gives us the formula of V equals, oops, wrong one. It gives us the D is equal to velocity times time. Base times height. Actually, this is going to be height times base. Height of the graph times the base of the graph. Okay, really cool. What's even more cool, we're only studying constant velocities, so we're seeing velocities that are straight line graphs. This also happens and works for velocity times graphs that are like this, which is all about chapter 2, which is changing velocities. And, oh, hold on, this rule also works for university. Okay, it also helps for university because you could calculate using calculus this area under there, this velocity and time graph, the area under this curve. Advanced math can calculate that, and that'll be its change in displacement. So this rule here that I'm just going to highlight in yellow is amazingly powerful. Okay? More powerful than the equations we're using. In fact, we get the equations to use through this rule. If we had to say which came first, the chicken or the egg, okay, which came first, this graphing or the formula? The graphing comes first, because the formulas come from this graph. Okay, so that's the number 2 rule, and the number 1 rule was the slope of a position time graph is the velocity. Mr. Curl, you mentioned grade 12 or next chapter, and you mentioned university. So if the position time graph was like that, could we get the slope anywhere and determine that it's velocity? And the answer is true. At this point, the slope of that line, the slope of this line, the slope of that line, the slope is always changing here, but the slope will give us the velocity at that point, the velocity at that point, the velocity at that point. So this rule number 1 is as important and as powerful as that rule number 2. There's graphing for you. Okay.